Thanks for the introduction. Good morning, everyone. So my presentation is on construction of 4D cortical surface atlas for the Baby Connect project. This is a preliminary study. So the research background is that during the early postnatal stage, the human brain development is very dynamic with region-specific growth. However, from this longitudinal T1 and T2 structured images, we can see that the image contrast is very low, and the image appearance, brain size, shape, property change dynamically. That means for infant brain analysis, we will require infant dedicated computational tools and brain atlases, since most of existing tools and atlases are developed for adult brains. So for cortical surface-based analysis of the infant brain, infant surface atlas plays a fundamental role. So basically, the surface atlases encode the spatial appearance and the label information for cortical surface registration, the spatial normalization, and the inter-subject, inter-study comparison. However, given the dynamic development during early postnatal stage, it is required to make the atlas age-matched and densely sampled. So previously, we have constructed and released the first 4D infant surface atlas. We have the atlas at every 3 months in the first year and every 6 months in the second year. So those are publicly available on the NITRIC website. However, we do notice there are certain limitations. First is given the dynamic development during the early post months, especially the first half year, it would be better to make atlas month by month. Second is that when we construct this atlases, the image resolution is about 1 millimeter. It is not high enough. So with the recent progress in the Baby Connect project, this is one of the NIH-funded Lifespan Human Connect project. There are 2 sites in this project, the UNC Chapel Hill and the University of Minnesota. So we will scan about 500 children, and the age is between 0 to 5 years. This is accelerated longitudinal diagram. We can see the image resolution is very high. For example, for structured image, we have 0.8 isotropic resolution. For the resting state, we have 2 by 2 by 2 resolution. So this is comparable to the HCP project. So this study aims to construct 4D cortical surface atlas densely sampled from birth to 5 years of age by using the high quality image from the Baby Connect project. And we also want to preserve sharp cortical folding patterns on these atlases. So in this preliminary study, we use 410 longitudinal T1, T2 images with 0.8 isotropic resolution. They are from 212 subjects. This table shows scan distribution at each month, but this is about 1 year ago. So right now we have more subjects and more scans at each age. For image processing, we use an established infant dedicated surface analysis pipeline. So given the T1, T2 structured images, we will do the processing to remove non-brain tissues and cerebellum. Then we will do the deep learning-based tissue segmentation. And then we will also correct topological errors by using a deep learning-based method. And after that, we will reconstruct the inner cortical surface and outer cortical surface by using deformable surface model with topology property. After that, we will calculate cortical attribute, average convexity, mean curvature, gyrification, circle depth, cortical thickness. We will also map everything onto a physical space for our atlas construction. So all those cortical surfaces are represented by a triangle mesh. There is one-to-one correspondence between the inner surface and its spherical surface. After that, we will need to establish the anatomic correspondence across subjects and across scans. So here we adapt the group-wise registration method by using spherical demos. And once we align them together, the anatomical location are roughly moved to the same location. After that, one simple strategy for atlas construction is just to do the Euclidean average. But the problem is that because the Euclidean average is sensitive to the potential registration errors, so in this way we will get a blurred folding pattern. So this will degrade the registration performance. So our aim is to replace this step by using the Washington barycenter, because it encodes the transport information when we measure distances, so it's robust to the potential registration error. In this way, we will get a sharper folding pattern. So let's give you a toy example. So we have two subjects. This is the cortical attribute distribution. And if we do, here there are slight misalignment between them, but if we will do simply Euclidean average, we will get the yellow profile, but anatomically and geometrically, this is not very meaningful. So our aim is to use the Washington barycenter, because this is a geometrically more meaningful mean under the Washington distance metric. So in this way, the atlas is robust to the potential registration errors. So mathematically, we can formulate it in this way. We have a set of subject distribution in terms of cortical attributes, and we want to find the mean. We call it Washington barycenter and the Washington distance. So here, the Washington distance measures distance between any two normalized distribution and the theory of optimal transportation. However, this is a non-convex problem. It's very hard to find a solution. To make the problem easy to solve and to make it convex, so we adopt the entropy penalized. So we have three terms. One is the transportation matrix and its associated cost matrix, and also entropy penalty. So by doing this, the problem became convex, and we can easily get a solution. So this is reconstruct the surface atlas from 2 months to 9 months. It's a month by month atlas. We have every convexity, mean curvature. We also have the circle depth, but I didn't show it here. So we can see during the first 9 months, there are region-specific changes, especially in the high order association area. And this atlas from 12 months to 16 months, we can see even after 1 year, there are still substitution changes, and also the development pattern is region specific. So this movie shows goose pattern in terms of average convexity, circle depth, mean curvature. They are all aligned onto the age-matched average cortical surface. We can say the change is very dynamic, especially during the first months. We also do a comparison with the conventional method, that's average-based atlas. So this is atlas constructed by the average-based method. We show the convexity and the mean curvature. We can see the folding is a little blurred, but if we use the proposed method, the folding pattern is very sharp, which indicated the proposed method lead to sharper folding pattern. This will potentially lead to better registration performance. If I switch these two slides, you will better see the difference. So in conclusion, we have constructed a set of 40 cortical surface atlas for the baby connector project. By using the Washington distance, this constructed 40 surface atlas preserve sharp folding pattern. This will lead to improve the registration performance in comparison to use the conventional average-based method constructed atlas. In our future work, we will further improve this atlas to more validation, both quantitative and qualitative. And we will also release this atlas to the public, and meanwhile we will also create the parcellation maps. Finally, I would like to thank all the parents and the babies who contributed to this project, and also our funding support from NIH. Our post number is T131. Thank you.